Okay, today we're looking at base e, and all a natural log is a log with a base of e. E is just a number. It's like 2.71 and a whole bunch of decimals. It goes on forever, just like pi does. So we just use e as we go throughout. Exponent properties with base e. This is just like the exponents we did back in the first semester. If they both have, so here we have e to the x times e squared. If they both have the same base, then you're going to add their exponents. So this would be e to the x plus 2. We're just looking at exponent properties here. This is where we say e to the a times e to the b is the same thing as e to the a plus b. When we divide, numbers just divide as always. 6 divided by 8 is 3 over 4, reduces to that. Here we've got e cubed over e. When we simplify that, we'd get e squared. If you remember, we'd do an exponent of 3 minus an exponent of 1. So that would give us the e squared. So this is e to the a over e to the b equals e to the a minus b. Here when we square root, we're going to square root each piece. You need to think, that's probably the easiest way to think of it, is either square rooting each piece or raising this to the power of 1/2. So this would be 16 equals 16 to the 1/2 power times e. Here we're multiplying because this exponent's out on its own. E squared. 16 to the 1/2 power is the square root of 16, which is 4. So we get 4e squared. Here you've got e to the a. Property is when we have our power of powers. So e to the a to the b is the same thing as e to the ab. Finally, when we deal with the negative exponents, this exponent's got to go to everything, but it goes to 3 to the negative third power, not 3 times negative 3, 3 to the negative third, e to the positive 6. Don't forget negative exponents make fractions, so this 3 to the negative 3 would come down to the denominator as 3 to the positive 3, which is 27. E to the 6, because it's positive, it's going to stay on the top. So we have e to the 6th over 27. Here you can think about e to the negative b equals 1 over e to the positive b. Expanding and condensing our properties of natural logs are the exact same as they were with the logs we just took a test over. So the natural log of a times b is the same thing as the natural log of a plus the natural log of b. When you expand, they both get their natural log. Multiplication becomes addition. Division, both get a natural log, and then b subtraction. Here the natural log of a to the c is the same thing as c natural log of a. So when we expand when we condense this first one, this 2 becomes an exponent, so we have x squared. 1/2 becomes an exponent, so we've got 9 to the 1/2. But we know that 9 to the 1/2 is the same thing as the square root of 9, which is 3. So we've got x squared, then plus will become multiplication. So our answer is natural log, because we condense it down to 1, of 3x squared. Okay, so the 2 came on as my exponent. The plus means multiply. 9 to the 1/2 power is 3. Here we expand. All of them get their natural log. So the natural log of x squared, but that squared needs to go in front, so we'd have 2 natural log of x. We're moving to the bottom, so minus the natural log of 2, but we also need to break up this 2 and y, because it's really 2 times y down there. So to keep it on the bottom, we're going to do minus again, natural log of y. Oops, you can't see that. Okay, the last thing we look at is continuously compounded interest. This is very similar to what we did before, except now instead of your interest being added on monthly or quarterly or semi-annually, it's added on every instant. It's constantly added on. This isn't actually possible. You can't go open an account that's compounded continuously. However, it kind of gives us the upper limit, the upper bound of what a regular compound interest problem could earn. So you could see what the maximum you could ever possibly earn would be. So when we do this, A is the balance of your account. P is the principal, but it's also called the deposit. It's how much you put in, your initial deposit. R is the rate. Make sure you do it as a decimal. And T is time. Okay, so we're using the equation PE to the RT. So A equals P times E raised to the power of RT. So we look at this, a student invests $2,000 in an account, that's what they put in, so that'll be our P. That earns 3.4%, so 0.034 will be our R. Interest compounded continuously, this lets us know we're going to use the E equation. We want to know the balance after 6 years, so that's our T. So we've got A equals 2,000 times E to the 0.034 times 6. Now when you type this into your calculator, I lost my calculator. Found it. When you type it into your calculator, you're going to do 2,000, and then right above natural log it says e to the x. If you want to put an exponent with e, which we do because we want to put 0.034 times 6, you're going to use that. So second natural log, that puts the e and the exponent in for us. 0.034 times 6. Hit enter. So after 6 years, we will have $2,452.60. Part B asks, how long will it take for the account to reach $3,000? So we want to know when the account is $3,000 for our final. We put in the 2,000 times e to the 0.034. Now we don't know how long, so we're going to use t as our exponent. Okay, we're just going to use t. Now we want to know about how long, so we're going to use our calculator to figure out about how long it takes to get to this $3,000. So I'm going to type this into my y equals equation. So if we go up to y equals, we've got 2,000 e, so second natural log of e raised to the power of 0.034, and we're going to use an x because that's what our calculator uses, x. And then if we go to our table, we're going to be able to scroll around in our table and see when our graph actually reaches $3,000. So if you notice, between year 11 we're at $2,900, year 12 we're at $3,007. So somewhere between 11 and 12 years is when we reach $1,000, but it's much closer to 12 because we're only $7 over. So we're going to say about 12 years to get to my $3,000 balance. All right, we're going to do some more of these and talk about them tomorrow in class.